Greetings, everybody. This is Dr. Gomez. Um, I've got here what I call it's a problem from Chapter 10. Chapter 10 is dealing with rotational kinetic energy and angular momentum. And I say it's a good study problem. And it's an application of conservation of angular momentum and conservation of energy. And this problem is posted on Georgia View right here. Um, but I thought I'd post this video and give you some insight into how to approach it because there's a problem very similar to this on exam 4. So what's going on is you have a uniform cube, mass large M, width 2a, and it's moving with a speed of v and sliding on this frictionless table. And there's a small lip at the end of the table. So when the cube hits that lip, it begins to rotate about that. Begins to rotate with some angular speed omega. And we want to find the minimum value of the linear speed v such that the cube just barely tips over and falls off the table. And I give you a couple of hints. Hint number 1 is that the cube undergoes an inelastic collision at the lip. So when the cube hits the lip of the table, that's an inelastic collision. And so remember, for an inelastic collision, because this is rotational motion, angular momentum is conserved. And so part of hint 1 says apply conservation of angular momentum immediately before and immediately after the collision. And then because the collision is inelastic, kinetic energy is not conserved. So we have to apply conservation of energy, but only after the collision. And we'll get into that in more detail. Then the second hint is that for a uniform cube, mass large M, width 2a, the moment of inertia through the center of mass of the cube is 2/3 ma squared. Well, we want to use the parallel axis theorem to get the moment of inertia of the cube about an axis through one edge. Well, that's already done. That's posted in the lecture notes. That's this right here, moment of inertia of a uniform cube. And so you can go ahead and look at that. But we use the parallel axis theorem because when the cube hits the lip of the table, it's going to be rotating about an axis, in this diagram, about an axis through AB. And so this problem details how to use the parallel axis theorem to get that moment of inertia. And you get 8/3 ma squared. So we know that remember, this ICM, that means that's the moment of inertia about an axis through the center of mass. We want it about an axis through one edge, and it's 8/3 ma squared. So now let's go ahead and again, we want to solve for the minimum value of v in terms of g and h. We're going to get an algebraic expression, not a numerical value. But I want the minimum value for v such that the cube, when it hits the lip and it rotates, it will just barely tip over and then fall off the table. And again, you use the parallel axis theorem to get the moment of inertia about a cube pivoted through one edge. So here I go from the notes. We know that I is equal to 8/3 ma squared. Now let's look at hint number 1. Let's apply conservation of angular momentum immediately before and immediately after the collision. So L initial is equal to L final. Well, remember, the initial angular momentum, we treat the cube as it's approaching the lip. We treat the cube as if all its mass is centered at the CM. Remember, when I say CM, I mean the center of mass of the cube. Don't confuse it with the fact that the mass of the cube is large M. Don't let that confuse you. Just when I say CM, I'm referring to the center of mass of the cube, which we know is going to be right at its exact geometrical center. So as the cube approaches the lip, The angular momentum, we treat the cube as if all its mass is centered at its CM, geometrical center. So the perpendicular distance between the velocity vector and the rotation point right before it hits the lip, that perpendicular distance is a. Nothing complicated. So the initial angular momentum is mva. M is the mass of the cube, v is the velocity, a is what we call the perpendicular distance between the velocity and the rotation point. Well, after the collision, the cube begins to rotate with some angular speed omega. So my final L final is simply I omega. Well, what is I? 8/3 ma squared. Okay, so we have Li equals Lf. MVA equals I omega. MVA equals 8/3 ma squared omega. Now what we want to do with this conservation of angular momentum equation, we want to solve it for V. Why? Well, what's the problem asking for? The value for V. So the basic algebra, V is 8/3 a omega. I'll call that equation 1. Okay, now let's apply conservation of energy to the block, but only after the collision. It's somewhat similar to the ballistic pendulum. With the ballistic pendulum, it's conservation of momentum immediately before, immediately after. And then it's conservation of energy only after. Well, very similar here. It's only conservation of energy after the collision. Well, let's look at this figure below. And here, so this is after the collision. So at the instant the cube hits the lip, it's going to begin to rotate with an angular speed omega. The cm of the cube right now is at a height of a above the table. Well, then what's happening is the cube rotates. Well, when it hits the tipping point, when we say just barely tips over, what we mean is that it's going to stop for an instant at the tipping point and then fall off the table. So at the tipping point, omega is 0. It balances there for that split second in time and then just tips over. Well, at the tipping point, the cm is directly above that point, right at the tipping point. Well, at that tipping point, the height of the cm is a√2. Well, now this is after the collision. This is the instant in time right after the cube hits the lip and begins to rotate, and this is when it's at the tipping point. Conservation of energy. Well, here, as it begins to rotate, the cube has rotational kinetic energy, 1/2 I omega squared, and the cm of the cube has gravitational potential energy, mga. We're using the table as our reference point. So the cm of the cube is at a height of a above the table. So that's the rotational kinetic energy immediately after the collision. Then again, the mga term, that's the potential energy of the center of mass immediately after the collision. Well, then at the tipping point, the cube is stationary for that millisecond in time. So there's no kinetic energy, but the potential energy of the cm is now mg a√2. Remember, in general, gravitational potential energy is mgh, where h is the height above or below the reference point. So this is the conservation of energy equation. 1/2 I omega squared plus mga equals mga√2. Okay? Well, let's go to the next line. Let's look at the 1/2 I omega squared term. Well, what is I? 8/3 ma squared. So we have 1/2. Remember, the 1/2 is there. Don't let the algebra confuse you. It's not complicated. That's my 1/2 I omega squared. Plus mga equals mga√2. Well, nothing complicated. The 1/2 and the 8/3, that gives you 4/3. So you have 4/3 ma squared omega squared plus mga equals mga√2. Well, what is our goal? With the conservation of energy equation, when we apply conservation of energy immediately only after the collision, not immediately after, it's just conservation of energy after the collision. Well, our goal is to get an expression for omega that we can then put into equation 1. So our goal is, with the conservation of energy equation, our goal is to get an expression for omega. So going back, we have 1/2 8/3 ma squared omega squared plus mga equals mga root 2. So you get, in the algebra, you get 4/3 ma squared omega squared plus mga equals mga root 2. The big M cancels. You get 4/3 a omega squared plus g equals g root 2. And just take this equation, algebraically solve for omega. You get equation 2. I'll leave the steps to you. It's just algebra. But you get omega is 1/2, and then you have the radical, 3g, then in parentheses under the radical, root 2 minus 1 all over a. Now we take that expression for omega and put it back into equation 1. And I've rewritten equation 1 on this next page. So this is equation 1. V, we got V is 8/3 a omega. And in the green, what is omega? Well, from the conservation of energy, we got omega was the green term in parentheses. And then this expression, the 8/3 a times this term in parentheses, that gives you 4, and then square root, and then under the radical you have ga parentheses root 2 minus 1 over 3. And if you're a little bit confused as how to go from this step to this one, let me know. But the idea is you apply conservation of angular momentum immediately before and immediately after the collision, and you want to get an expression for V. It's going to be in terms of omega. Then you apply conservation of energy after the collision, as indicated in this figure here, and you want to get, using the conservation of energy, you want to obtain an expression for omega, which you can then put into equation 1. And again, we get that the minimum speed necessary, V, is 4, then square root, then ga parentheses root 2 minus 1 over 3. And that's it. So that's, I'm going to save this video and get it posted. And again, there's a problem very, very, very similar to this on exam 4. Alrighty.